Welcome folks to a video discussing advanced applications of integrals. In this video, we're going to be having a look at linear differential equations. So we'll talk about what makes a differential equation linear. We'll identify a strategy for solving those differential equations, and then we'll see some examples. And just a reminder here, we're talking about first order differential equations here. So first order linear differential equations is the focus of this discussion. Here's a motivating problem. Let's have a look at this first order. It turns out it's a linear differential equation. We'll see why it's linear in a second. X squared dy dx plus 2xy is equal to 5. Now we can see that this is a differential equation for the unknown function y, which is a function of x. Now I've sort of rigged this equation up in a special way so that the left-hand side has a special form. If you stare at it for a moment, and I'll invite you to press pause and see if you can identify anything interesting here, what you should see is a product rule. You should see the first function times the derivative of the second plus the derivative of the first function times the second. So I'll go ahead and use our prime notation to denote that. I'm going to write the left-hand side as x squared y prime plus 2xy. We can think of this as x squared y prime plus the derivative x squared prime times y. Now, we're pretty accustomed to going this way with the product rule, and it turns out to solve these linear differential equations, we're going to undo our product rule instead to write a product rule as the derivative of a formal product. Okay, so I'll use this undoing of the product rule, or recollecting those terms, to express our differential equation in a condensed form. So here I've rewritten our differential equation using that product rule above as x squared y all prime equals x to the fifth. Now we can integrate both sides here with respect to x. X squared y all prime dx is equal to the integral of x to the fifth dx. And keep in mind here that this prime denotes a derivative with respect to x, right? So if we have a derivative with respect to x, integrated with respect to x, we're just going to get back that thing that we took the derivative of. So here's that last computation, and we'll see how we can find an explicit family of solutions here. So again, integrating both sides with respect to x, recognizing that we have a derivative with respect to x, and recognizing that we can quickly integrate x to the fifth to obtain 1/6 x to the sixth. We can then divide by this factor of x squared and see that the solution here is y of x equal to 1/6 x to the fourth plus some arbitrary constant over x squared. Using our terminology from before, we would call this an explicit family of solutions. Okay, so here's that explicit family of solutions again. Y of x equals 1/6 x to the fourth plus c over x squared. And we know it's an explicit solution because y is explicitly a function of x. And we know it's a family of solutions because it's true for any value of this arbitrary constant c. So the question is that you might have, is this sort of magic always possible? And the answer is maybe. Under what conditions is it possible? And it turns out that this magic is always possible if we have a first order linear differential equation. How do we do it? How we do it ends up being sort of a magical factor called the integrating factor. We'll see in a minute. The integrating factor is a magical factor that changes a first order linear differential equation into a product rule. Once we have that product rule, we know that we can integrate both sides, and away we go. Okay, so let's talk about what makes a differential equation linear. A first order differential equation is linear if it has form a1 of x times dy dx plus a0 of x times y equals some function, say g of x. Okay, these functions a1, a0, and g, it turns out, can be anything they want. Okay, so by linear, what we mean here is linear in the dependent variable or the unknown function and its derivatives. So again, with the unknown function y as a function of x, linear means we only see dy dx. We only see y. We don't see any non-linearities in dy dx or y. Again, those functions a, 0, a1, and g can be whatever they want, as long as we only have dy dx and y. Makes a differential equation linear. Okay, any linear differential equation we can write in the following normal form. This is a normal form for a linear differential equation. Just divide both sides by a1 of x, and we can express our linear differential equation as dy dx plus p of xy equals q of x. And this is always going to be the starting point for investigating our linear differential equations. So in beginning to manipulate a linear differential equation, we'll always have to start right here. Once we arrive at this form, it's quick to see that magical, mystical factor I mentioned before called the integrating factor from our linear differential equation right here. And be careful, any sign attached in front, you have to attach to the p of x too. The integrating factor is e to the integral of that thing in front of the y, p of x dx. So this p of x is the same p of x. Okay, so that p of x is critical in identifying the integrating factor. Do an integral of p of x and express our integrating factor as e to any antiderivative of that little p of x. We're calling the antiderivative capital P of x. Here's how it works once we have the integrating factor. Once we have the integrating factor, multiply both sides of that normal form by mu of x. You should, if you rigged everything up correctly, see a product rule on the left-hand side that you can condense and integrate both sides with respect to x, just like we saw before. Okay, so let's see an example that uses this strategy. Oh, by the way, a couple remarks. This process typically yields a one-parameter family of implicit solutions, but those implicit solutions, it turns out, are always a little bit easier to solve for the explicit solution, unlike our separable equations that we saw before. Okay, let's have a look at the example dy dx equals x plus 2y. This, as it turns out, is a linear differential equation for the unknown function y is a function of x. To see that, we'll express it in that normal form we mentioned before, dy dx minus 2y equals x. So in this case, minus 2 plays the role of p, and x plays the role of q. So let's go ahead and compute the integrating factor. The integrating factor is e to the integral of little p of x dx. So here again, I've used minus 2 as our little p of x, expressing mu of x as e to the integral of minus 2 dx. We just end up with e to the minus 2x. So according to our strategy, multiplying through our differential equation by this factor of mu of x should reveal a product rule. Let's check it out. So here's our differential equation, multiplying through by our integrating factor, mu of x. We see that e to the minus 2x dy dx minus 2 e to the minus 2xy is equal to x e to the minus 2x. Now, sure enough, here's our product rule right here, right? We can see we have the first times the derivative of the second plus the derivative of the first times the second. We can simplify that left-hand side, undoing our product rule and rewriting it as the derivative of a product equals the right-hand side, which in this case is x e to the minus 2x. So here's that product rule, e to the minus 2xy all prime is equal to x e to the minus 2x. We'll integrate both sides with respect to x, keeping in mind that this prime is a derivative with respect to x. Now you see one curveball here, and that curveball is we have a factor of x e to the minus 2x on the right-hand side that we'll have to integrate using integration by parts. So I won't go through that in all of its gory detail. I'll trust you to be able to use integration by parts to find an antiderivative there. Again, just use u equals to x, dv equal to e to the minus 2x dx, and write it out. Here is an implicit family of solutions. So the implicit family of solutions is e to the minus 2x times y equals the quantity minus 1/2 x minus 1/4 times e to the minus 2x. Again, this comes from integration by parts plus an arbitrary constant c. Dividing by e to the minus 2x, or equivalently multiplying through by e to the 2x, we see the explicit solution. Again, here's our explicit family of solutions. Y of x equals minus the quantity 1/2 x plus 1/4, all plus some arbitrary constant times e to the 2x. Okay, when we have an initial value problem, it turns out it's usually pretty straightforward to pick a member of that implicit family of solutions to satisfy an initial condition. Let's go ahead and see an example. This is sort of an outline of the strategy to solve an initial value problem where our unknown function is determined by a linear first order differential equation. Okay, so again, find that one parameter family of implicit solutions, satisfy the initial condition, and then, if possible, which with linear differential equations, it's usually pretty straightforward, write the explicit solution. Here's an example. Let's solve the initial value problem. Dy dx equals x plus 2y, where y of 1 is equal to 5. Okay, so we saw previously an explicit family of solutions to this differential equation. So again, here's that explicit family of solutions. Y of x is minus the quantity 1/2 x plus 1/4 plus an arbitrary constant c times e to the 2x. If y is equal to 1 when x is equal to, y is equal to 5 when x is equal to 1, we can solve for our constant c. In this case, we see that y equals 5 at x equals 1 gives the equation 5 equals minus the quantity 1/2 plus 1/4, all plus a constant times e to the 2. We can solve that for this constant as this constant c is 23/4 times e to the minus 2. Substituting that in, we'll see the explicit solution of the initial value problem. So here's that solution. Y of x is minus 1/2 x plus 1/4, all plus 23/4 times e to the 2 quantity x minus 1. And we can see here, condensing that exponential is nice using our rules of exponentials, and it's pretty quick to see that when x is 1, y is 5. So we satisfy the initial condition. Okay, let's do one more example here before we quit. Here's an example. Let's solve the initial value problem. Dy dx is 3 times the quantity 70 minus y. Now, this isn't obviously a linear differential equation, but a little bit of manipulation shows that it is. So let's check that out. So here's our differential equation written in first order linear normal form as dy dx plus 3y equals 210. Now, we know that our p of x here is going to be 3, our q of x is 210, so our integrating factor will incorporate that p of x. So here's our first order differential equation after computing the integrating factor e to the 3x and multiplying through by that integrating factor. We should see a product rule on the left-hand side, and we do, because here is the first times the derivative of the second plus the derivative of the first times the second. Condense that product rule, integrate both sides with respect to x, and see what happens. So here we see again our product rule condensed, integrate both sides with respect to x, recognizing our prime here is a derivative with respect to x. And in this case, the right-hand side integrates quickly as 70 e to the 3x plus an arbitrary constant. Solving for our explicit solution, we can see our explicit family of solutions here given by 70 plus an arbitrary constant times e to the minus 3x. You might recognize this solution from our video on separable differential equations, and it's quick to see that if x equals 0, c has to be 70, and that gives us the solution to the initial value problem. So here's that computation. If y of 0 is 100, c is 30, gives us the solution to the initial value problem. Y of x is 70 plus 30 e to the minus 3x. Okay, folks, hope you've enjoyed this video on linear first-order differential equations. Just a quick introduction. Have a great day, and we'll see you next time. Bye-bye.